Hey there, welcome back. Um, Today we're going to talk about programming the SIR model that we introduced in class. Um, let's first compare the way that our population model uh, looks compared to our SIR model. So in our population model, the way we simulated population growing over time is we had our population. We created a function that took in our population at time t and outputted the population at time t plus 1. As we went from time t to time t plus 1, we used an update function or a growth function to figure out what's going to be the population time t plus 1 as a function of population of time t. Similarly, we figured out what was going to be the population at time t plus 2 as a function of which we use the same function to figure out what the population time t plus 2 was as the population at time t plus 1. And as you continue this, you get a simulation for the population for all values of time t. In the SIR model, then things are slightly different because we don't just have one population, we have three populations. So we have S of t, I of t, and R of t. And then what we're doing is we're updating these values from time t to time t plus 1 through some functions, through the functions that are determined by the dynamical system that come with the SIR model. And so then instead of being time t, now we have the values at time t plus 1. And we apply the same update function to figure out what the populations are at time t plus 2. All right, and so we'll remember here that S represents the percentage of the population that is susceptible, who haven't had the disease and can possibly contract the disease. I is the percentage of the population who is infected, and R is the percentage of the population that is recovered. And what's happening is that over time these percentages are changing. And so let's draw our stock and flow diagram where we have S to I to R. What we determined was how do you transition from one state to the next? You transition from S to I by getting infected. And the way we determined how likely it was you're going to get infected was we said that was going to be equal to some constant times the percentage of people who are susceptible times the percentage of people who are infected. And we can think of this beta as being a product of two different parameters. It corresponds to both the transmission of disease, so how likely it is that the disease passes from one person to another. So proportion of disease being transmitted. And so it matters how likely it is that the disease passes from an infected person to a susceptible person, and it matters the proportion, the interaction. So the proportion of interaction between the populations. So how likely is it that a person who is susceptible comes in contact with a person who's infected? So this beta Si is this likelihood that somebody who's susceptible becomes infected. And then how likely is it that we transition from being infected to being recovered? So this is our recovery from being sick. And the rule of thumb that we set up here was, we said, if recovery takes D days, then we expect that gamma, which is equal to 1 over D, that percentage, that proportion of the population would get better every day. So if we're modeling how many of the people who are in I get better, then we say it's going to be gamma times I is this recovery rate, the number of people who recover. And so what we did is we took this and we incorporated this into a dynamical system, or a differential equations, set of differential equations, where we say ds dt is equal to negative beta times s times I, di dt is equal to positive beta times s times I, minus the number of people who recover, gamma times I, and we have that dr dt is equal to plus gamma times I. And our goal for today is to say that we're going to model these and we're going to put these into Python code. So these dynamics will be modeled in Python code. All right, so in order to do this, we're going to set this up similar to how we were doing the population model, which is we're going to have some system object that's going to keep track of all of our system parameters. So create a system object to keep track of our system parameters. So we will need to keep track of, so here's our system object. So we'll need, just like in the population model, we'll need to keep track of the time. So one of the things we'll be doing is we'll be assuming that our population, that our simulation starts at time 0. So one thing that maybe if you're working on your projects in the future, you may need to put an initial time in here. But we're basically going to assume that the time when we run our simulation starts at time 0. All right, then we'll need a time end. So the end time is going to be the time about how long the simulation lasts. And in the simulation in this book, we're saying that we're having a semester that's 14 weeks long. So 7 days a week, 14 days in a 14 weeks in a semester means that this is how long the simulation runs for. We'll need a beta parameter. We'll need a gamma. which is the gamma parameter. And so those values are going to be determined by the sickness that you're working with, depending on how likely it is that somebody will get infected and how long it takes for people to recover. And something new here is that before we needed our initial population. And in this situation, we still need our initial population, but our initial population has multiple pieces of it. And so here's something new that we're going to do for this model and for any model that requires keeping track of multiple populations at the same time, and that's to put a state object inside the system object. So we've got this system object. It has some initial parameters, some parameters that are defining the system, but it also has this initial state. And this thing isn't changing over time, right? This is the state of how many people start out susceptible, infected, and recovered. So S is the initial S percentage, I is equal to the initial I percentage, and R is equal to the initial R percentage. This is a fixed part of our system. Given the way that our system is set up, we start off with this initial value and our initial beta and our gamma and our given end time. And then as we see the system evolve over time, the number of people in each of the states is going to be changing over time, but this initial value, this initial population distribution is not changing over time. And so the reason why all of these things are bunched into the system is that these are the variables that are underlying our simulation. So we will create a function that makes our system object. And that takes as input our beta and gamma parameters. All right, so we're going to create this. We're going to define make system given beta and gamma. And what is it going to do? It's going to create our initial state object. So init is equal to state. Well, we'll first put in how many people are in each of these states. So there's a total number of 90 people on campus, one of whom is infected. And then we will convert these to percentages. So we're going to do init divided by equals init.sum. So this is going to take the total number of people, the sum of these values, add them all together, and it's going to then normalize. So after we run this, it's going to then have 89 divided by 90 as S, 1 divided by 90 as I, and 0 divided by 90, which is 0 in the recovered state. And then we're going to, we've taken in these parameters, beta and gamma, and we're going to return our system object that makes us happy. So our initial value here, our initial state right here is going to be defined here. We're defining what our end state is, 7 times 14. Our end time, not our end state. We're defining what our beta parameter is. It's whatever was passed in to our function. And we're defining gamma to be whatever was passed into the function. All right, and this creates our initial, this contains our system object that we will pass into the function. This is a good place to stop. We'll come back and talk about how we update these over time. See you shortly.